Hello everyone, welcome. So I think I'm audible. So this is lecture number one of calculus. So I hope everyone have seen the schedule. So the schedule for today is limits and indeterminate forms. So I'll try to complete limits and indeterminate forms in this class. If not, I'll extend. I'll give one more class on this. Right? Okay. So first, what I'll do is first I'll show you the syllabus of calculus. So this comes under this comes for almost 40 to 60 marks, depending upon. Okay. Okay. So I have shared my screen. So this is calculus session number one. So where I'll be covering very detailedly about limits and indeterminate forms, right? So after this lecture, what I will do is I will send you a material. Uh, I send you a material that consists of many problems from the topic which we discussed today. So you just solve all those problems from tomorrow, right? After that, we will go lecture by lecture. We will do this, right? Okay. So first, what I'll do is I'll show the syllabus. So calculus has been split into two parts. The one is a differential calculus and integral calculus. uh, I'm starting with the assumption that everyone knows basic differentiation, right? So basic 11th standard, 12th standard differentiation. So those are very basic ideas. I'm assuming that everyone knows basic differentiation. I'll be giving you formulas, but I'll not teach you how to differentiate, right? I'll be differentiating, but it's not that beginner course where I teach you how to differentiate, right? So I'm assuming that everyone knows how to do a basic differentiation in mathematics, right? Okay. You can see that calculus have been divided into two parts. One is differential calculus and other is integral calculus. So first we will be covering differential calculus, where the first topic is limits, continuity, and differentiability, followed by mean value theorem, Taylor theorem, and indeterminate forms, right? So in this class, there is some link between the this limits and just a minute. So there is some different link between this limits and indeterminate forms, right? Limits and indeterminate forms. This is what we're going to cover in this class, right? I'll try to cover as much as I can. If not, we will extend one more session on this topic where I'll be covering continuing limits and indeterminate forms, right? Okay. I think we can start, right? So first I'll give you, see, my lecture will be slow and steady. So it may take time, but you will have a very good conceptual understanding. You can do any problems from limits and indeterminate forms after seeing this required sessions, right? Okay. So we'll get into the topic, right? So first what I'll do is I'll give a basic introduction to what is meant by limits. And then I'll say you how to, there are many evaluation techniques to find limits. So we'll start, right? Okay. Okay. So first, what we'll do is we will start with the definition of limit, and then we will proceed, right? Okay. Say I want consistency from you, right? So you have to attend all classes, and then you have to do all the tasks which I'm giving you. So I'll be giving some materials also after this class. So I hope everyone will finish all those materials also, right? Okay. So first, what we'll do is we'll start with the definition of limits, right? So limit of a function. So limit of a function. Okay, so let us consider a real valued function, right? So let us consider a real valued function f from R to R. So we have a function f that your domain is a real number and your codomain is also a real number, right? So domain is you set off all inputs and codomain is where your inputs are matching to, right? So I have a real valued function. So we say it is a real valued function because your input is real number. So your input is real number. So if your input is real number and your output is also real number, then we say that function is a real valued function. So consider a real valued function, right? See, there are many functions which are not defined at some points, right? For example, let us consider the function f of x equal to sin x by x. Let us consider the function f of x equal to sin x by x. Now, what happens when you put x is equal to 0? We have a function f from R to R. So we have a real valued function. I'm taking an example of f of x equal to sin x by x. Now, what happens when you put x is equal to 0? It will become 0 by 0, right? See, because when you put x is equal to 0, so sin 0 is 0, and here when x is 0, it is 0. There are many functions like this, right? For example, you consider the function f of x equal to, let us say you consider the function f of x equal to 1 plus x whole power 1 by x. Now, what happens when you put x is equal to 0? What happens when you put x is equal to 0? So it will be like 1 power infinity, right? It will tend to 1 power infinity. So there are many functions which are not defined at some points, right? Not defined at some point means the output is not defined, right? The output is not defined. Let us take the function. There are many functions like this, right? So f of x equal to, let us consider tan x by x minus pi by 2. Now, what happens when you put x is equal to pi by 2? What happens? This at x is equal to 0. This is at x is equal to 0 again. At x is equal to 0, sin x by x will tend to 0 by 0. So it is not defined. And similarly, if you consider f of x equal to 1 plus x whole power 1 by x, when x is 0, it will tend to 1 point infinity. Again, it is not defined. And similarly, if you consider f of x tan x by x minus pi by 2, what happens when x is equal to pi by 2? Tan pi by 2 is infinity, right? Because tan pi by 2 is sin pi by 2 by cos pi by 2. So sin pi by 2 is 0, cos pi by 2 is, sin pi by 2 is 1, cos pi by 2 is 0. So it is 1 by 0, it is infinity. So it will tend to infinity by infinity, right? It will tend to infinity by infinity when x is equal to pi by 2. So there are many functions which are not defined at some points, right? See, if you consider sin x by x, 0 is the only point that is troubling us. When you put 0, it is sin 0 by 0. For all other values of x, the function is defined. If you put x is equal to 1, it is sin 1 by 1. Yes, output is defined. If you put x is equal to 1 lakh, sin 1 lakh by 1 lakh. Yes, output is defined. So it is defined for all x except for some x, right? For example, this function is not defined at x is equal to 0. This function is not defined at x is equal to 0 again. So there are many functions which are not defined at some point. We are interested in those kind of functions, right? We are interested in those kinds of functions, right? So let us consider a real valued function f that is from R to R, right? Let us consider, I'm going to consider two type of functions now, right? I'll draw a diagram. Just a minute. See, if you have any doubt, you just post a message on the chat session. So I will do this. Okay. So let us consider some two kinds of functions. Just a minute. Okay. Let us consider some two kinds of function, right? Let us say this is our function f, and let us say it is not defined at this point, right? Let's say this is a point x is equal to a. Let us say the function is not defined at this point, right? See, not defined at that point means the output is not defined. So the output can be like the output can be like it can be 0 by 0, or it can be infinity by infinity, or it can be 1 per infinity, right? Or it can be 1 per infinity. Whenever you have these kinds of, just a minute. Yes. So it is of the form 1 per infinity. And let us say the output is of the form 0 power 0. And let us say the output is of the form infinity power 0. So these, we call this as indeterminate forms, right? So whenever the output is like this, we say the function x, the function f of x is not defined at that point, right? So like this, when you put, we have a function f of x, At x is equal to a, it is not defined. Just I'm doing some whole here. That means the function is not defined at that point, right? And similarly, let us consider one more function here. Let us say at x is equal to a, at x is equal to a, again the function is not defined, but it is like this, right? It is like this. It goes like this. Now, I have two different functions. Let us say this is our example one. In both the examples, the function is not defined. The function is not defined at x is equal to a. In both the example, the function is not defined at x is equal to a, right? Now, what is our aim is, see, we know the function is not defined at x is equal to a. My aim is, I want to see what happens in the neighborhood of a. That's it. Exactly at a, the function is not defined, but I want to know where f is approaching in the neighborhood of a, right? I want to see, I want to find. See, we know that f is not defined. We know that f is not defined at x is equal to a. But I'm interested in, but I'm interested, what happens. I'm interested, what happens in the neighborhood of a. What happens in the neighborhood of a. This is what I'm interested in, right? So even though f is not defined at a, but I'm interested what happens in the neighborhood of a. Right? See, we are talking about real valued function. We will be studying complex analysis also. Here my domain is real number. That means we can approach this point. We can approach this point either from left or from the right. Right? We can approach this point either from the left or from the right. So since my domain is real number, I can approach this point A to the left or from the right. Right? So we know that f is not defined at A, but I'm interested what happens in the neighborhood of A. So neighborhood here means only from the left side, from the right side. But if you do complex analysis, the neighborhood can be anywhere, right? It can be any curve. But in a real valued function, my neighborhood is left and right. Now, what I'm doing is exactly at A, f is not defined. F is not defined. Now, I'm going to approach this point A from the right first, right? Let us say this number is 5, right? Just for example, I'm giving you 5. Let us say this number is 5. Let us say this number is some 7, right? Okay. Now, consider the first example. In the first example, even though f is not defined at A, if I approach A from the left, you can see the function is approaching this point, right? If x is approaching from this side, you can see your f is approaching this number, right? So it is not defined at this point, but it is coming very closer to this point. And similarly, when I approach A from the left, you can see my curve is approaching in this direction, and again both are approaching a same number in this graph. In this graph, here the function A is not defined at that point. At x is equal to, function is not defined. But in this graph, if I approach A from the right and from the left, both are approaching the same number in this graph. But in this graph, you can see at x is equal to A, when I approach from the left, you can see my function is approaching this number, which is 5, right? And when I approach A from the right, output is here, and you can see the function is approaching 7. So in these two examples, from the first example, even though x is not defined at A, but when I approach A from the right and the left, both are approaching the same number. Again, this example 2, again f is not defined at A, but at A, when I approach from the left, it is approaching 5. And when I approach from the right, it is approaching 7, right? It is approaching 7. Now, we want to define something new called what is meant by limits. So even though f is not defined at A, what we are interested is what happens in the neighborhood of A. We say limit exists at this point. Even though f is not defined at A, we say limit exists at that point if your left hand limit and the right hand limit both are approaching the same number, and that number has to be finite number also. Now you can see at x is equal to a, the function is not defined, but limit exists for this function at a. Why? Because your right hand limit is approaching 5, and your left hand limit is also approaching 5. So even though f is not defined at a, if both the function are approaching the same number from the right and from the left, then we say limit exists for that function at that point. But when you look at this example too, at x is equal to a, when you approach from the left hand side, the function is approaching 5. And when you approach when you approach a from the right hand side, it is approaching 7. So they are not equal. 5 and 7 are not equal. In this case, we say limit does not exist. In this case, we say limit does not exist. Now, we're going to define what is meant by limit of a function. We say limit exists at x is equal to a if your left hand limit is equal to right hand limit and both are finite number. See, LHL is called left hand limit, and RHL is right hand limit, right? Right hand limit, right? So whenever if these two numbers are equal, then we say limit exists at that point, right? Okay, just a minute. I'll stop my. Okay, now you can see. I'll explain again. At x is equal to a, the function is not defined. Exactly. Let us say this is your x-axis and this is your y-axis. Let us say at this is a point a. At a, the function is not defined. That means when you put x is equal to a, the output is not defined. The output is not defined means the output can be like 0 by 0 or infinity by infinity. There are many indeterminate forms. But even at exactly the function is not defined. But I want to know what happens where f is approaching the neighborhood of a. So all I'm going to do is I'm going to approach this point a from the right hand side. You see where f is approaching, and you approach this point a from the left hand side. You see where f is approaching. If both are approaching the same number, right? See, exactly at this point is not defined, but if both are approaching the same number, then we say, just see this diagram. So both are approaching the same number. This is your right hand limit, this is your left hand limit. Both are approaching the same number. If both are approaching the same number and both are finite number, then we say limit exists at this point. If one is going to some other number, the other is going to some other number, then we say limit does not exist because your LHL and RHL are not equal. So we say limit exists at x is equal to a if your LHL and RHL both are equal and both are finite, right? Both are finite. Now, diagrammatically, I have explained where limit exists. But now what I'm going to do is we're going to derive the definition of LHL and RHL, right? LHL and RHL. Okay. Okay. Now, what I'm going to do is, let us say we have a function y. Let us say at this point, the function is not defined, right? Let us say this point is x is equal to a. Let us say this point is equal to some L, right? It is some L. Now, at exactly a, the function is not defined, right? At exactly a, the function is not defined. As you can see, I have put some hole at x is equal to a. Now, what happens in the neighborhood of a? That is what we are interested in. Now, what I'm going to do is, let us take a positive quantity h that is greater than 0. Let us take a positive quantity h that is greater than 0. Now, let us say this point is, let us construct two new points. I'm taking a positive distance h. This distance is h. So this point will be a plus h, right? This distance is h and this point is a plus h. From a, I'm moving right, h units to the right. And similarly, you take the same distance h, you move to the left. This point is a minus h. Now, a plus h, the corresponding function value is here, which is f of a plus h. And for a minus h, the corresponding function value is here, which is f of a minus h. Now, first, what I'll do is, we will find right hand limit. First, we will find right hand limit. Okay. Now, what I'm going to do is, I'm going to approach this a from the right. I'm going to approach A from the right. So from the right, I'm going to approach. Now I want to bring this A plus H closer to A. If I bring A plus H closer to A, then this f of A plus H will become very closer to this undefined points. Yes or no? If I bring A plus H very closer to H, very closer to A, this f of A plus H will become very closer to this undefined point. Now, how I can bring A and A plus H very closer? If the distance between these 2 points is very small, then I can bring f of A plus H very closer to this undefined point. Yes or no? See, if my this is your A plus, if this is your H, then this is your A plus H, and this point will be your f of A plus H. Now you can see this f of A plus H is closer to this undefined point. Now, if this distance is very small, let us say this distance is 0.1 billion 1, 0.1 billion 1, 0.0000 100 billion 0 followed by 1. Then can you imagine how the distance between A and A plus H? At exactly A only function is not defined. Very closer to next to A also function is defined. Now I want to reduce this distance. This distance has to be very small. First, what is the distance between these 2 points? This is A plus H. This is A. What is the distance? It is modulus of A plus H minus A, right? Distance between the 2 points, x2 minus x1. So this distance is modulus of H. That we already know because from A, we have moved H units to the right. So distance is H. So if the value of H is very small, if the value of H is very small, then this f of A plus H will become very closer to this undefined points. How small has to be H? It has to be very small that the value of H should be very closer to 0. Then only your A and A plus H will be very little apart. So what I'm going to do is I'm going to derive the formula for right hand limit. So f of A plus H is your function value. Now I need to bring this f of A plus H closer to this undefined point. For that, I'm going to put limit s tending to 0. So if limit s tending to 0 happens, then you can see that in this f of A plus H, so in this f of A plus H, if I put s tending to 0, then this point will become closer to this point. And similarly, I'm going to define what is your left hand limit. What is your left hand limit? So limit s tending to 0, f of A minus H, right? You can see f of A minus H is your left hand function, right? This is your left hand function, f of A minus H. Now you have to bring this very closer to this point. Again, similarly, this H has to be very small. How small? It has to be very small. That H is tending to 0, right? If this happens, then both the points will become very closer to this point. If both the points are approaching the same point, we say limit exists, right? So limit x tending to A, f of x exists. So at A, the limit exists if LHL, RHL both are equal, exists if LHL is equal to RHL and both are finite, right? So that is, if you want to find limit x tending to f of x, you need to find LHL. So LHL is limit s tending to 0, f of A minus H. And if you want to find RHL, if you want to find RHL, you need to find limit s tending to 0, f of A plus H. So you need to find both these, you need to evaluate both the limits. If both are equal, then we say limit x tending to A, f of x exists. See, we talk about limit only when this at A the function is not defined. At exactly the function is not defined. What happens when x is tending to A? If x is tending to A, since we are in real valued function, it can tend either from the right or from the left. So you just find RHL, you find LHL. If both are equal, then we say limit exists at that point, and both has to be finite also. Right? This is the definition of limit of a function. Now, in all the cases, for all the functions, it is not that easy to find LHL, it is not that easy to find RHL, and you have to find the if I give you any function, first you have to find LHL, you have to find RHL, and if both are equal, then it's a limit exists. For all function, it is not that easy to find LHL and RHL. And also it is time consuming also. We need to find LHL, we need to find RHL. If both are approaching same number, then it's a limit exists at that point. It is time consuming. So there are many techniques to evaluate limits, right? So limits evaluation techniques. So evaluation techniques of limits. So there are many evaluation techniques of limits. So first technique is, we can find limits using definition, right? The first technique is by definition. By definition. That is, by definition means you need to find LHL, you need to find RHL. If both are equal, limit exists and limit is equal to that value. This is time consuming. And the second is, we can evaluate limits using standard formulas. We can evaluate limit using standard formulas. So if you are prepared for a IDJ in class 12, you would have come across standard formulas, right? Standard formulas. And also, you can evaluate limits using L'Hopital rule, right? L'Hopital rule. L'Hopital rule. And also, we can evaluate limits using Maclaurin series. So these are the four major techniques that we will take to evaluate limits, right? So by definition, mostly we will not use definition. We will use definition in continuity differentiability to find limits. But to evaluate limits, mostly we will go for either standard formulas or L'Hopital rule. For L'Hopital rule, you need to have basic understanding about how to differentiate a function, right? Now, I'm not going to focus on this LHL, RHL, and both are equal, limit exists, and limit is equal to that value. We will be focusing mainly on standard formulas and L'Hopital rule. This L'Hopital rule, this is called indeterminate forms, right? That is how to perform limits when the form is indeterminate. That can be solved also, right? These are the four major techniques to evaluate limits. First, I'll give you standard formulas, right? I'll give you standard formulas. Then we will do L'Hopital rule. I'll give you an introduction to L'Hopital rule. Then directly we will jump into the problems, right? Okay. But mostly we're going to do problems only on standard formulas and L'Hopital rule. Here I will solve. Okay. This kind, by definition, we will be doing in continuous differentiability, not in here, right? I'll solve more problems by definition when we do continuous differentiability, which is our next topic. As of now, we'll be focusing on standard formulas and L'Hopital rule. So first, what we'll do is I'll write down some standard formulas. Standard formulas. Okay. The first standard formula is limit x tending to a sin f of x by f of x is always equal to 1, provided your f of x tends to 0 as x tends to a. Whenever you see sin f of x by f of x, you can always close your eyes and put that function as value is equal to 1, provided your f of x as tend to 0 as x tends to a. I'll give you an example. Let us consider limit x tending to 2 sin of x minus 2 by x minus 2. What is your f of x here? It is x minus 2, right? Sin f of x by f of x. So your f of x is x minus 2. And what happens to x minus 2 when x is tending to 2? It is 0. So sin f of x by f of x. And your f of x is tending to 0 as x tends to 2. So I can close my eyes and write this value as equal to 1. And what about limit extending to 3 sine of x minus 3 by x minus 3. I can close my eyes and write that value to be equal to 1 because it is sine f of x by f of x. So sine f of x by f of x is 1 provided your f of x tends to 0 as x tends to a. Now consider, can I write what about sine x by x? What is your f of x? Your f of x is 1 sine f of x by f of x. After sine, that is your f of x, and same function has to be in the numerator denominator also. Whatever you have f of x, that has to be here also. Again, I can write this value as equal to 1, right? And what about limit extending to 1 sine of x minus 2 by x minus 2? Can I write this as 1? No, because what is your f of x? Your f of x is x minus 2. When x is tending to 1, your f of x is tending to minus 1. That is not tending to 0. So for this, you should not put this to be equal to 1. You can apply standard formula only when your f of x is tending to 0 as x tends to a. Okay. The second standard formula is limit extending to a tan f of x by f of x. This also equal to 1 provided your f of x tends to 0 as x tends to a. Similarly, if I replace all this sine by tan, again it will be equal to 1 also. Tan f of x by f of x, and your f of x should tend to 0 as x tends to a. Third, limit extending to a log of 1 plus f of x by f of x. Again, this is equal to 1 provided your f of x tends to 0 as x tends to a, right? See, we will be doing this in problem, then you will understand. Limit extending to a e power f of x minus 1 by f of x. This limit is also equal to 1 provided f of x tends to 0 as x tends to a. Limit extending to a power f of x minus 1 by f of x. This is also equal to 1 provided your f of x tends to 0 as x tends to a, and this is the approximation of binomial approximation. Limit extending to a 1 plus f of x whole power n is approximated to 1 plus n into f of x provided your f of x tends to 0 as x tends to a. These are 6 major 99% standard formulas that you can use in performing limits, right? Whenever you have log of 1 plus f of x by f of x, I'll give you an example. Whenever you see these kinds of function, limit extending to 0, log of 1 plus 2x by 2x. What is your f of x here? 2x. 1 plus f of x by f of x. Your f of x is 2x. And that 2x is 10 to 0 as x tends to 0. So I can write this as 1. Right? Okay. I'll give you some examples of how to use standard formula. Right? Some examples. We are not doing problems. I'll give you many cases where you will be using standard formula. Let us consider you have limit extending to 0 sine 3x by 4. Let us say this is into x, right? Multiplied by tan 4x by 4x square into x by 2. Let us say I'm just writing whatever I'm getting. Let us say you want to find this limit. Now, whenever you see sine 3x, you have sine f of x, right? You have sine f of x. So sine f of x by f of x, I can write that as 1. Provided your f of x tends to 0 as x tends to 0, your f of x is 3x that tends to 0. What I'll be doing is, I'll be multiplying and dividing 3x. Now, the sine 3x by 3x, I can write that, I can take that term fully, I can write that term to be equal to 1. And here I have tan 4x. Your f of x is 4x. That tends to 0 when x is 0 because 4 into 0 is 0. What I'll be doing is I'll be multiplying 4x and then multiplying 4x. And I can take this tan 4x by 4x. I can take that outside and I can put that as 1 again. So after, see, I have removed some odd functions, that is sine I have removed, tan I have removed. So I'll be left with limit x tending to 0, 3x by 4x into 4x by 4x square into x by 2. This x will get cancelled, x square will get cancelled. So you will be having 3 by 4 into 1 by 2. So 3 by 8 is your limit, right? I'll give you many examples. See, we're going to do many problems, but I'm telling you this how to apply standard formulas, right? For example, let us consider limit x tending to 0, log of 1 plus 2x divided by sine 3x multiplied by e power 2x minus 1. Let us say this is tan 4x, right? Let us multiply, let us have some sine square 3x divided by, or I can write 2. Let us say we have x square here. Let us say we have to find this limit. Now, here I have log of 1 plus f of x. But log of 1 plus f of x divided by f of x is missing. But your f of x is 2x. That tends to 0 as x tends to 0, right? So what I'll be doing is, whenever I see this, what I'll be doing is, we have log of 1 plus 2x. What I'll be doing is, I'll be multiplying and dividing by 2x into 2x, right? I'll be multiplying and dividing by 2x into 2x. And here I have divided by sine 3x. I'll be multiplying and dividing by what? 3x, 3x. And here I have e power 2x minus 1. I'll be multiplying and dividing by 2x, right? Because I know e power f of x minus 1 by f of x is 1. So what I'm doing is I'll be multiplying and dividing by 2x. And here I have tan 4x. I'll be multiplying and dividing by 4x. And here I have sine square 3x. Very important. Whenever you have square here, you have to multiply and divide by f of x whole square. Whatever you have power you have to multiply and divide by that power. All this you can see all are power 1. But here you have sine square 3x. So multiply and divide by f of x whole square. Suppose if I have sine cube 3x, multiply and divide by 3x whole cube, 3x whole cube. Divided by 2 into x square. I can close my eyes and can write this value to be 1, this value to be equal to 1, this value is equal to 1, this value is equal to 1, this value is also equal to 1. Because I can write this as sine 3x by 3x whole square. So what I'll be left with? I will be left with, here I have only 2 by 3. Here I have only 2 by 4. Here I have, see, okay, let us write this here x, let us write x square in the denominator, right? Instead of x square here. See, I'm generating a question, that's it. See, I'm generating my own question, right? If you are very comfortable in limits, you can generate many own questions, right? When you look at this, it will be very complicated for you. But when you know standard formulas and when you know how to apply limits, these are very easy. Now this will become 9. This will become 9, and this x square will get cancelled. This will become 9 by 2, right? So this is your required limit. 2 will get cancelled. And this will be 18 by 12, right? So 18 by 12, so which is 3 by 2 is the required limit. So are you comfortable now? See, we're going to do many problems, but can you just visualize the importance of standard formulas, right? Yes, I'll pause here. Is there any doubt up to now? See, we're going to do many problems. I'll tell you how to evaluate limits using standard formulas. Whenever you have sign of something, multiply and divide by that something, remove that sign term. Whenever you have tan of something, multiply and divide by something. Whenever you see tan f of x, whenever you see tan f of x, you multiply and divide by f of x and remove the tan f of x by f of x. You can do that only when f of x tends to 0 as x tends to 0. right? And whenever you see e power f of x minus 1, you multiply and divide by f of x and remove that full term e power f of x minus 1 by f of x, right? Okay. Is there any doubt up to now? See, just try to express, right? That's why I have some closed group. Instead of taking in YouTube, see, if I go in YouTube, I'll get views. But I'm going in closed group just because to get more interactions, right? If you want, you can also unmute and talk. Okay. Okay, I'll also give that permission. Now you can unmute yourself if you have any doubt. Okay. Okay. Now, yes, sir.
Can you just show me the standard formula once again?
I just take a screenshot. I'll send notes also after this.
Okay, fine. Thank you. All right.
Okay. Now, what I will do in this, I'll be introducing L'Hopital rule now, right? I've been introducing L'Hopital rule now. Standard formulas we have covered, right? We gone to many problems, but for the understanding, you know what is standard formulas, right? Now, what L'Hopital rule says, right? What L'Hopital rule says is, so we have a L'Hopital rule. Okay, so what L'Hopital rule says is, yes, if you have limit extending to a, let us say we have a function like this, f of x by g of x. F can be any function, g can be any function. When you apply the limit a, either the function is of the form 0 by 0 or infinity by infinity, right? Let us consider the same example. Let us consider limit extending to 0, sin x by x. What happens when you apply the limit? It is of the form 0 by 0. So whenever you have f of x by g of x, and when you apply the limit, if it is of the form 0 by 0 or infinity by infinity, so what L'Hopital rule says is, this limit is same as you differentiate the numerator, you differentiate the denominator separately, again you apply the limit. Separately, I'm using the word separately, that is very important. You differentiate numerator separately, differentiate denominator separately, apply the limit, right? Apply the limit again. Again, if it is 0 by 0 or infinity by infinity, continue the process. What I have to do? Again, you differentiate the numerator f double dash of x. Again, you differentiate the denominator g double dash of x. Continue this process. Continue this process until you get a finite number. Until you get a finite number, right? This is what L'Hopital rule says. Now, I know everyone knows basic differentiation, right? Basic differentiations. Okay. So first is d by dx of x power n into x power n minus 1. d by dx of sin f of x. d by dx sin f of x is cos f of x into f dash of x, right? d by dx of sin f of x is cos f of x into f dash of x. I'll give you an example. What is d by dx of sin of 3x plus 2? So sin f of x, what is your f of x? 3x plus 2. So cos f of x into f dash of x. What is the derivative of 3x plus 2? It is 3. d by dx of sin of x square. What is your f of x here? It is x square, right? Sin f of x. Your f of x is x square. Just substitute in the formula. It is cos x square into, what is your f of x? X square. What is the derivative of x square? It is 2x. And similarly, what is d by dx of cos f of x? It is minus sin f of x into f dash of x. I'll give examples. d by dx of cos of x square plus 2x plus 1. What is your f of x? F of x is x square plus 2x plus 1. What is the derivative of cos f of x? Minus sine f of x. So minus sine f of x into f dash of x. X square derivative is 2x, 2x derivative is 2, and 1 derivative is 0. Now, d by dx of e power f of x. d by dx of e power f of x. E power f of x into f dash of x, right? Now, what is d by dx of? Okay. Now, what is d by dx of e power x square? Your f of x is x square, so e power x square into f dash of x, so it is 2x. Now, what is d by dx of e power sine x? E power sine x, f of x is sine x, e power sine x into f dash of x. Derivative of sine x is cos x, right? Okay. Now, next is d by dx of log f of x. 1 by f of x into f dash of x, right? I'll give you examples. What is d by dx of? What is d by dx of log 3x? What is your f of x? It is 3x. So 1 by 3x into f dash of x. Derivative of 3x is 3. What is d by dx of log of sin x? What is your f of x? It is sin x, log f of x. So 1 by sin x into d by dx of sin x is cos x, right? Okay. Now next is d by dx of a power x. A is constant. So d by dx of a power x. So it is a power x log a. It is a power x log a. D by dx of root f of x. It is 1 by 2 root f of x into f dash of x. I'll give you examples. What is d by dx of root of sin x? What is your f of x? It is sin x. 1 by 2 root sin x into what is your f dash of x? It is cos x, right? Here I'm generalizing and giving you all formulas. Root f of x. Your f of x is sin x. So 1 by 2 root f of x into f dash of x. Okay. Sin cos. And then d by dx of tan f of x. It is secant square f of x into f dash of x, right? There are many formulas, right? But these are many standard formulas, right? And then d by dx of cosecant x, cot x. You just go through all the, just brush up all the differentiation formulas. And whenever you have product of two functions, x into sin x, whenever you have plus, you can take d by dx inside. Differentiation satisfies linear property. You can linearity property. You can take d by dx inside. But if you have product, how to differentiate? So let us call this function as u. Call this function as v. So it is u into v dash plus u into v dash. See, I'm assuming that we don't know basic differentiation. So u is x, v dash, derivative of sin x is cos x, v sin x, derivative of x is 1. So the derivative is x cos x plus sin x. And if you have x divided by sin x, so it is this is called as product rule. If it is in product, how to differentiate? This is called quotient rule. So it is v into u dash, u into v dash divided by v square. Your u is x and v is sin x. So v is sin x, u dash is 1, u is x, your u is x, v dash is cos x divided by sin x whole square. This is called quotient rule. Right? These are basic differentiation that you would have come across in 11th and 12th, right? Okay, just a minute. So you have written all the basic differentiation formulas. Just take a screenshot and then write it down, right? So this is also important. F of x whole power n into f of x whole power n minus 1 into f dash of x. Just a minute. Okay, so this Maclaurin series, I'll come back to this later. Now what I'm going to do is we're going to do some many problems based on how to find limits using indeterminate forms, right? Okay, the first set of problem that we're going to do is how to find the limits when the limit is of the form 0 by 0, right? This is what we're going to focus first. Okay, is there any doubt up to now? Yes, so we'll start doing problems. Okay, so we'll start doing problems. Problem 1. Limit x tending to 0, x minus tan x divided by x cube, right? X minus tan x divided by x cube. See, whenever I try the whenever I see the problem, I try to apply standard formulas, right? I try to apply standard formulas. I will eliminate all these tan x and so on, right? Okay. See, but the problem is if you apply standard formula, in the numerator, this will become tan x. We'll multiply and divide x and x, right? In that case, your numerator becomes 0 x minus x. That is problem. What I'm doing is, if I have tan x, usually what you will do, we'll multiply x here, we'll multiply x here. This will be equal to 1. But we should not do here, because then this become x minus x. That is a problem now, right? In that case, you don't do this. Okay. In that case, you don't do this. Okay. So x minus, sorry, it is not tan x. Just a minute. The question is, okay, it is correct. Okay. Okay. Suppose what we'll do is we'll start with the, okay. So we have x minus tan x by x. Now, when you apply the limit, you can see this of the form 0 by 0, right? Because 0 minus tan 0 is 0, and here is 0. So I can apply L'Hopital rule. So you differentiate this. Derivative of x is 1. Derivative of tan x is secant square x. Derivative of x cube is 3x square. Is the first step is clear? See, just remember this, all this, right? And just write this page after the class. So derivative of tan x is secant square x divided by 3x square. Now what happens when you put 0? Again, this is 0 by 0. Because secant 0 is again 1. So secant 0 is 1 by cos 0. So again 1 by cos 0 is again 1 by 1, which is 1. So again it is 0 by 0, right? Now again we will differentiate. Limit x tending to 0. Derivative of 1 is 0. Now what is derivative of secant square x? So it is secant x whole square, right? Now what is d by dx of f of x whole power n? N into f of x whole power n minus 1 into f dash of x. I think it's not visible if I write here. What is d by dx of f of x whole power n? N into f of x whole power n minus 1 into f dash of x. Now what is d by dx of secant x whole square? So f of x is secant x. So 2 secant x whole power 2 minus 1 into d by dx of secant x. What is d by dx of secant x? It is secant x tan x, right? In secant x tan x. So this is 2 secant x into secant x tan x. So this is 2 secant square x into tan x. So this will become, the derivative of secant square x is 2 secant square x tan x whole divided by derivative of 3x square is 6x. Now we have limit x tending to 0 minus 2 times secant square x tan x divided by 6 times x. Now, can I combine this tan x by x and can I write this as this is equal to 1? Because we know tan f of x by f of x is equal to 1. And also your f of x is tan x that tends to 0. So we left with minus 2 by 6 secant square x. When you apply the limit, it is secant square 0 is what? It is 1. So minus 1 by 3 is your required limit, right? Because see, when you apply the limit, it is finite number. That is a limit. So this is minus 1 by 3 into the secant square x will tend to 1. When x is 0, is secant square 0. So secant square 0 is 1. So it is minus 1 by 3 into 1. So minus 1 by 3 is your required limit, right? So we'll do many problems. So problem number 2. Limit x tending to 0. Limit x tending to 0. X minus sin x. X minus sin x divided by tan cube x. See, what I will do is, we have tan cube x here. I'll apply standard formulas. You cannot apply standard formula in the numerator, because when you apply numerator, it will become x minus x. Here I have tan cube x. What I will do is, what I have to do now, what should I multiply and divide? Can anyone chart? See, it will be visible to only me only, right? You can chart. Here I have tan cube x. What I need to do? I need to multiply and divide by what? X cube. Good. I need to multiply and divide by x cube. So we'll multiply and divide by x cube. See the importance of standard formula. Tan cube, if you don't know standard formula, you have to differentiate tan cube x in L'Hopital. That is very tricky. But differentiating x cube is very easy. I can strike this and I can put that value to be equal to 1. So we have limit x tending to 0, x minus sin x by x cube. Now it is 0 by 0, right? So I can apply L'Hopital rule. Derivative of x is 1. Derivative of sin x is cos x. See, whenever I write 0 by 0, next step I'll be differentiating. Remember that. Derivative of x square is 3x square. When you apply the limit, again it is 0 by 0, right? Because cos 0 is 1. 1 minus 1 is 0 by 0. So again we'll differentiate. What is derivative of 1 is 0. Derivative of cos x is minus sin x. Derivative of this is 6x. So you will be having limit x tending to 0, sin x by 6x. Again it is 0 by 0, but you don't need to differentiate. Sin x by x. Your sin f of x by f of x. Your f of x is x. That tends to 0 as x tends to 0. So this will be equal to 1. So you will be having 1 by 6 is your required answer. Is it clear? Okay. So we'll move on to problem number 3. Limit x tending to 0, 1 minus cos x divided by 3x square. Can you perform this limit and just differentiate and tell me the answer? 1 minus cos x divided by 3x square. Just differentiate. It is 0 by 0 form. So I'll give you some 30 seconds. Very easy. Good. Good. I see 2. What about others? See, make yourself engage. Then only the time will go, or else it will be very tough for you. 1 by 6. Good. So how you will do? It is 0 by 0. Now derivative of 1 is 0. Derivative of cos x minus sin x whole divided by 6x. So you have sin x by 6x. Sin x by x will tend to 1. So it is 1 by 6. You don't differentiate cos x by 6. Again, apply the limit. That is not needed. Okay. But you have to quote the standard formulas, whatever you are writing. Problem 4. Limit x tending to 0, x square plus 2 cos x minus 2 whole divided by x into sin cube x. Yes, what you will do by seeing this, what you will do in the first step? Is there any possibility of applying standard formula anywhere? By seeing this, what you will do? Is there any possibility of applying standard formula anywhere? You have sin cube x here. Multiply and divide by x cube, right? Multiply and divide by x cube. See, that is very important. You don't just multiply and divide by x. It is x cube. So x cube, x cube. This will become 1. Now this is equal to limit x tending to 0, x square plus 2 cos x minus 2 divided by x power 4, right? Yes. Now again it is 0 by 0 form. It is 0 by 0 form. So we have limit x tending to 0. What is derivative of x square? It is 2x. Derivative of cos x minus sin x, and this will become 0, and this will become 4x cube. So we have limit x tending to 0, 2x minus 2 sin x divided by 4x cube. See, don't apply standard formula now. If I multiply and divide by x, this will become 1, but numerator will become 2x minus 2x. Don't do that, right? Don't do that. Okay. Let us this be sin x. Let us this be sin x. Okay. Now this is equal to limit extending to 0. It is 0 by 0 form. Derivative of 2x is 2. Derivative of sin x is cos x whole divided by, this is 12x square. So again it is 0 by 0 form. So this will become limit extending to 0. Derivative of 2 is 0. 2 times derivative of cos x is minus sin x whole divided by, this is 24x, right? Derivative of x is 24x. Now we have limit extending to 0, 2 sin x by 24x. The sin x by x will become 1. So we have 1 by 12 is your required limit. 1 by 12 is your required limit. Yes. So problem 5. Limit extending to 0. Limit extending to 0. 1 minus cos x whole divided by x into log of 1 plus x. Is there any possibility of applying standard formula anywhere? Is there any possibility of applying standard formula anywhere? In the numerator, you can see it is log of 1 plus, we have, in the numerator, we have log of 1 plus f of x. You can see log of 1 plus f of x. You can apply standard formula 3, right? Log of 1 plus f of x. But denominator f of x is missing. Log of 1 plus f of x by f of x. So we know that limit extending to a, log of 1 plus f of x by f of x is equal to 1, provided your f of x tends to 0 as x tends to a. What I'm going to do is limit extending to 0, 1 minus cos x whole divided by log of 1 plus f of x. But f of x is what is here? F of x is x. Let us multiply and divide by x. So log of 1, see, we can apply standard formula only when f of x tends to 0 as x tends to a. Your f of x is x, that tends to 0 when x is 0. This will become 1. So we have limit extending to 0, 1 minus cos x by x square. See how easy this become after applying standard formula. If you don't know standard formula, you have to differentiate this using product rule, L'Hopital rule. Okay. So this is 0 by 0 form. So limit extending to 0, derivative of 1 is 0, derivative of cos x is minus sin x, derivative of x square is 2x. So we have limit extending to 0, sin x by 2x, sin x by x is 1. So 1 by 2 is your required limit. Right? Problem 6. Limit extending to 0, log of 1 plus x cube whole divided by sin cube x. Is there any possibility of applying standard formula in the numerator? Is there any possibility of applying standard formula in the numerator? We have log of 1 plus x cube, multiply and divide by x cube, multiply and divide by x cube. Is there any possibility of applying in the denominator? Multiply and divide by x cube again. This will become 1. This will become 1. And overall, the limit will become 1. You know standard formula, what you will do? You have to differentiate this log of 1 plus x cube, 1 by f of x into f dash of x. This is 3 sine square x into cos x, derivative of sine cube x, f of x sine x whole power 3. So 3 sine x whole square into cos x. You take reduced time. Okay. But you have to quote the standard formula, whatever you are writing. Problem 7. Limit x tending to 0, e power x minus e power x cos x whole divided by x minus sin x. Okay. This is something lightly long. E power x minus e power x cos x by x minus sin x. Denominator, you can apply standard formula, but it will become 0 minus 0. That is trouble. Okay. What we'll do is we will apply L'Hopital rule directly. Okay. Now you know derivative of e power f of x is e power f of x into f dash of x. This is a derivative of e power f of x. Now it is of the form 0 by 0. So we have limit x tending to 0. Derivative of e power x is e power x. Derivative of e power x cos x is x cos x into d by dx of x cos x. E power f of x into f dash of x. What is d by dx of x cos x? You keep x as it is. Derivative of cos x is minus sin x. Plus you keep cos x as it is. Derivative of x is 1. Whole divided by derivative of x is 1. Derivative of sin x is cos x. Is this step is clear? Okay. Now I don't want sin x here. What I'll do is I'll multiply and divide by x. I'll multiply and divide by x. So this will become limit x tending to 0, e power x minus e power x cos x. This will become what? This will become minus x square plus cos x whole divided by 1 minus cos x. Is this step is clear? Okay, we have e power x minus e power x cos x, e power x cos x minus x square. Is there any mistake I have made? E power x minus e power f of x into, it is e power x cos x. Okay. Okay. E power x. Okay, is it correct? So we have limit x tending to 0, e power x minus e power x cos x minus x square plus cos x whole divided by, in numerator we can multiply and divide by x for cos x. No, for cos x we should not do. Only for sin x, tan x you should do. Standard formula is only for sin x and cos x, right? Sin x, tan x only you can do. Okay. Whole divided by 1 minus cos x. I'm just thinking of, say I don't want to differentiate. I'm just thinking of some other technique. Without differentiating, I'm just trying to simplify some more extent. I want to simplify the numerator because that is big. Okay, let us do this. I can simplify in denominator. 1 minus cos x is 2 sine square x by 2. Trigonometry. 1 minus cos x is 2 sine square x by 2. From that I can simplify numerator, but okay, let us differentiate once again. It is 0 by 0. So we have limit extending to 0. Derivative of e power x is e power x. Here I have to apply product rule. Let us keep this e power x cos x as it is. Derivative of this is minus 2x minus sin x. And let us keep this as it is, minus x square plus cos x. To differentiate this, e power x cos x and e power f of x into f dash of x. So x into minus sin x plus cos x whole divided by 0 minus sin x. Okay. So we have limit extending to 0, e power x. Now if I multiply this here, what do you have? Plus 2x e power x cos x. And if I multiply this here, you will have plus e power x cos x into sin x, right? And here we have minus x square plus cos x e power x cos x. This I can write this as let's multiply and divide by x minus x square plus cos x whole divided by sin x, right? Okay. Now again I have to differentiate, right? I think you can do this, right? Let's you have to differentiate this, apply the limit. You will get the answer in the next step, because when you apply the limit, derivative of sin x is cos x. So denominator will become 1 after applying limit. Denominator will become 1 after applying limit. So if you want, I'll just give the reference material. You just differentiate once again apply the L'Hopital rule, right? Move on to next problem. This is very easy. You can use this for reference, right? You'll get answer as 3. If you continue this, you'll get the answer as 3, right? Okay. So we'll move on to problem number 8. Problem 8. Limit extending to 0, e power x minus e power sin x whole divided by x minus sin x, right? Okay. So we'll do this. So we have limit extending to 0. So it is of the form 0 by 0, right? So don't apply standard formula here. If you apply standard formula, this will become xx, but this will become e power x minus e power x. That is problem for us, right? Okay. So we have derivative of e power x is e power x. Derivative of e power sin x is e power sin x into cos x whole divided by 1 minus cos x. 1 minus cos x. So again it is 0 by 0 form. So we have limit extending to 0. Derivative of e power x is e power x. Now we have to differentiate e power sin x cos x. Let us keep e power sin x as it is. Derivative of cos x is minus sin x. Plus let us keep cos x as it is. Derivative of e power sin x is e power sin x into cos x whole divided by, and the derivative of 1 is 0. Derivative of cos x is minus sin x. So we have limit extending to 0, e power x plus sin x e power sin x plus cos x whole square into e power sin x whole divided by plus sin x. Now what I'm going to do is I'm going to apply standard formulas. Here I have sin x, let us multiply and divide by x. Here I have sin x, let us multiply and divide by x. Here I have sin x, multiply and divide by x. Here I have x, multiply and divide by x. This will become easy. The differentiation will become easy. So we have limit x tending to 0, e power x. This will become what? This will become 1. This will become 1. So we have x into e power x. This will become x into cos x whole square whole divided by x, right? Whole divided by x. Now, if you perform limits individually, we have limit x tending to 0, e power x by x. No, you have to differentiate once again, right? Because it is of the form 0 by 0. Is there any mistake I have made? Okay, just see whether I made mistake anyway. So we have this is e power x and this is plus, this will become minus. Okay, here I made mistake. This will become minus and this is minus e power x cos x whole square, right? Okay. Now when you apply limit, this will become 1, e power 0 is 1, this will become 0, this will become 1 again. So again it is of the form 0 by 0. Let's differentiate this once again. Limit x tending to 0, derivative of e power x is e power x, derivative of x e power x. Let us keep x as it is, derivative of e power x is e power x. Let us keep e power x as it is, derivative of x is 1, minus, let us keep cos x whole square as it is, derivative of e power x is e power x. Let us keep e power x as it is, derivative of cos x whole square is 2 cos x into minus sin x. Denominator will become 1. Denominator will become 1. See, d by dx of cos x whole square. So d by dx of f of x whole power n. So it is n into f of x whole power n minus 1 into f dash of x. So it is 2 cos x into minus sin x, right? Okay. Now when you apply the limit, what will happen? This will be 0. This will be 0, right? This will be 1. This will be 1. E power 0 is 1. This will be again 1. So we have 1 plus 1 minus 1. So 1 plus 1 minus 1. So 1 is your required limit. 1 is your required limit, right? Okay. So problem 9. Limit x tending to 0, x into cos x minus log of 1 plus x whole divided by x square. What will you do? Is there any possibility of applying standard formula anywhere? Is there any possibility of applying standard formula anywhere? Limit x tending to 0, x into cos x log of 1 plus x, multiply and divide by x. Good. Multiply and divide by x. And here we have x square. Let us keep that as it is. So we have a limit x tending to 0, x cos x minus x divided by x square. So it is of the form 0 by 0. So limit x tending to 0. Let us keep x as it is. Derivative of cos x is minus sin x. Let us keep cos x as it is. Derivative of x is 1. Derivative of x is 1 divided by 2x. So we have limit x tending to 0, x into minus sin x plus cos x minus 1 whole divided by 2x. I don't want sin x. Let us multiply and divide by x. So this will become 1. So we have limit x tending to 0 minus x square plus cos x minus 1 whole divided by 2x. It is 0 by 0 form, right? It is 0 by 0 form. Let us multiply, differentiate this. So limit x tending to 0 minus 2x minus sin x divided by 2. When you apply the limit, what do you will have? Minus 2x. I think I made some mistake. Minus x square plus cos x minus sin x. Is there any mistake I have made? So we have x cos x. So x cos x minus x by x. So x into cos 1 minus sin x plus cos x x 1 1. So we have multiplying dividing by x. So we have minus x square plus cos x minus 1 by 2x. So if I differentiate, you will have minus 2x. I think I made some mistake. I'm getting answer. Limit x tending to 0 minus x square okay. If I try to apply standard formula, we are getting a 0 as an answer, right? We're getting 0 as an answer. Let us, what we can do is, let us not apply standard formula and then we'll try, right? Let us see I'm getting answer or not. Then I will discuss again why I'm not doing this. Let us apply standard, let us differentiate this and then we'll try to do this. But I think this will not affect the system. Okay, so we have limit x tending to 0. So let us keep this x as it is. Derivative of sin x is cos x. And let us keep this sin x as it is. Derivative of x is 1. And derivative of cos x is minus sin x whole divided by, this is 2. Again, I'm getting 0 only. I think I'm making some mistake. Okay. Why this method is not working? Because no, we cannot differentiate further because this you can see this become constant term, right? This has to be a limit. If I apply the limit, I'm getting 0 as an answer, but book it is given that answer is 1 by 2. I'll explain why this is not working here, right? I'll explain why this is not working here. Denominator we have second degree. If I apply standard formula, numerator is become linear. Yes or no? Numerator is becoming linear. So numerator is linear, denominator is quadratic. Obviously, limit will be equal to 0 only. Yes or no? So what I'll do is let us not apply standard formula here. And let us do this as let us differentiate this. Then this will become degree 2 by degree 2. Can you get my point? If I apply standard formula, denominator is degree 1, numerator is degree 2. So there is no possibility of getting non-zero limit. So what I'll do is let us differentiate this here. So we have limit x tending to 0. Let us differentiate this. X, derivative of cos x is minus sin x. Let us keep as it is. Derivative of x is 1. What is derivative of log 1 plus x? Log f of x, it is 1 by 1 plus x whole divided by 2x. Right? Whole divided by 2x. Now we have limit x tending to 0 minus x sin x plus cos x minus 1 by 1 plus x into 2x. Is it clear up to now? Is it clear up to now? Okay. What we'll do is we can cross multiply here. We cross multiply here, you will have minus x into sin x 1 plus x plus cos x minus 1 whole divided by 2x into 1 plus x. Or you can also differentiate this directly because you know the derivative of 1 by x, right? Or you can differentiate this, you differentiate once again. So it is 0 by 0. So we have limit x tending to 0. Let us keep this derivative of sin x is cos x. And derivative of, let us keep sin x as it is. Derivative of x is 1. And derivative of cos x is minus sin x. And what about the derivative of 1 by 1? Derivative of 1 by x is minus 1 by x square. So this will become 1 by 1 plus x whole square whole divided by 2. Right? Whole divided by 2. Now, when you apply the limit, what do you will have? This will become 0. This will become 0. This will become 0. This will become 1. So overall, you will have 1 by 2 as your limit, right? So d by dx of 1 by x is minus 1 by x square. Now here we have 1 by x. So instead of x, we have 1 plus x, right? Okay. See, why we are not using standard formula? Because if I use standard formula, numerator is becoming degree 1. Denominator is becoming degree 2. So in order to get limit, your x square term should cancel. Then only you get a finite number. But here I'm not doing this because I'm differentiating and I'm changing everything to degree 2. Right? Here we have degree 2. Here if I do this, this will become x, will become x. Here we have degree 1, here we have degree 2. That is why I'm not doing this. Okay. Okay. Can we do one more problem now? Problem 10. We have limit x tending to 0, e power x minus 2 cos x plus e power minus x whole divided by x sin x. Can you do this problem in your own? Two. Yes, good. Two, good. Yes, some. Anyone other than? Is anyone else all are getting the answer as 2? Should I want to do or you will do? You just comment, right? Should if I want to do, I will do. See here you apply standard formula. Here you apply standard formula. So let us multiply and divide by x. This will become x square. Just differentiate. Right? Two will be the answer. See, similarly for infinity by infinity also, you have to follow the same technique, right? You have to differentiate. You have to differentiate only, right? For infinity by infinity also, you have to differentiate only. Okay. See again, actually there are many forms. I have completed 0 by 0. Infinity by infinity is similar only, right? There are forms 0 power 0, 1 point infinity, 0 power 0. Three more forms are there. There are three more forms apart from this. And then finding unknowns in the limits, that is also there, right? That is also there. Another, it will take another 40 minutes to 1 hour to complete that. By schedule, live classes, it will be like, I think the next live class is on Wednesday, I think. So what I will do is, I'll keep one more class tomorrow evening. It will be just 1 hour. I'll complete the remaining forms. By tomorrow evening, what you have to do? What you have to do is, I'm going to send this material today. So I'm going to send this material today. That named as indeterminate forms, right? So if you go through this material, you can see the first form is where it is. Yes, the first form is 0 by 0 form. Yes, you can see that this is the first form is 0 by 0 form. I think I have also solved so many problems from here. You can see uh, there are 38, 40 problems are there, right? Don't need to solve all. If you got the idea, you can do any problem. You just try this. This problem alone you skip. Tomorrow I'll be doing this. Find the value of a and b in order that this limit is equal to 1. The limit is given. They are asking you the unknowns. This problem alone I will do. That is 42, 44, 45. All this I'll be doing. These three problems I'll be doing tomorrow, right? You skip these three problems. Again, you can see the second form. The second is infinity by infinity form. Infinity by infinity form. Again, you start doing this problem. Same. You have differentiate numerator, differentiate denominator. Apply standard formula wherever possible. I have given you all differentiation formulas. I'll share this book in the Telegram group. After finishing infinity by infinity form, it has only 15 questions. 0 into infinity form. 0 into infinity form can be transferred to 0 by 0 form, right? In that there are some and fourth form is infinity minus infinity form. You just take LCM, you will have either infinity by, if you take LCM of this, see for example, if you have infinity by infinity minus, if you take LCM, you will end up with 0 by 0 form or infinity by infinity form. If you know 0 by 0 form, same as it is extended to infinity by infinity form. Infinity minus infinity, if you take LCM for that function, it will again end up with 0 by 0 form or infinity by infinity form. So you complete these 4 forms within tomorrow 7 o'clock. Tomorrow, what I'll be doing is I'll be starting the forms 0 power 0, 1 power infinity, infinity power 0. This form I'll be starting. Make sure that you complete up to year. That is page number 16 of this. Complete the 4 forms 0 by 0, infinity by infinity, infinity minus infinity form, and 1 into infinity form. You complete these 4 forms. You skip that unknown problems. So tomorrow I'll be doing this topic 0, 0, 1.3 dt by 0. It will be very short class only, followed by that problems. Tomorrow I'll be doing. So within tomorrow you complete this forms, right? I share this in a Telegram group. Is there any doubt? We'll wind off. So today's class, what we did is, okay. So today what we did is we have introduced what is meant by limit. So limit exists only when LS and RSL both are equal to the same number. And then we have evaluation techniques, LHS, RHS, standard formulas, L'Hopital, Maclaurin series. Maclaurin series I haven't taught you. I will do tomorrow also. And then I given you standard formulas. And then based on standard formulas and differentiation formulas, we have solved 10 problems, right? So complete that material, whatever I'm sending. So we'll see in the next class. Thank you. Bye. Is there any doubt you can ask? Okay. Okay, thank you. Bye. I'll end this meeting.